This is Lab 3 Circuits, Physics 2212 by Samantha Hefner. Introduction. The purpose of this lab is to observe and predict the behavior of circuits containing resistors and capacitors, to use multimeters to measure the values of potential differences in conventional currents, and to examine the behavior of ohmic resistors and capacitors. The preview. The node and loop rules hold true, and additionally we see that the magnitude of current in an RC circuit is time dependent. The fundamental principles and models. We're going to look at conservation of energy and charge, primarily through Kirchhoff's laws, which include the node rule and the loop rule. Additionally, we're going to do Ohm's law, which shows that V equals I times R, the capacitance, which C equals Q charge over V, and the idea that time dependence in resistor-capacitor circuits. So this is just a visual model of some of our fundamental principles. So here we have our loop rule, here we have the node rule, and then here we have Ohm's rule. So here's an image of the experience we set up. We have our two multimeters, we have our batteries here, and it's all connected to a resistor that's in a series on this side, even though it's a little bit hard to see. So this is kind of a visual representation. So we have the battery right here, our resistor right here, and then additionally not shown are our two ammeters right here. So our system is our battery plus our resistor circuit, and then our surrounding is going to be everything else. Our initial readings on our ammeters showed 19.2 MA. Okay, so what happens when we convert one ammeter to a voltmeter? What happens is the voltmeter reads 3.1 volts and the existing ammeter reading was virtually zero. And this happens because the voltmeter has very high resistance, inhibiting the flow of charge through the ammeter. What happens if we measure potential differences across circuit elements? So from A to B across the battery, we have a plus 2.88 volts. Then after we go through the first resistor, we lose 1.96 volt, and then through the second resistor, we do minus 0.92 volts. If you sum these all together, it equals 0, so we see that the circuit follows the loop rule. So here is this visually kind of represented in our graph. Why doesn't the ammeter reading change when you attach the voltmeter? This is because very little current flows through the ammeter because the voltmeter has such a high resistance. Here is our RC circuit. Here's a diagram of it, and then here's the one that we set up in the lab. Here we have our capacitor or our light bulb to help us visually see it. We have a resistor, and then we also have our battery. So when collected, the light charges and then it discharges. It took about 5 seconds to charge it and about 40.9 seconds to gradually discharge. And it kind of follows a linear decline path down in response to time. Some possible sources of error could include human error and accurately starting and stopping the stopwatch. We could get a faulty ammeter/voltmeter reading, or we could have just had an error in setting up the circuit. What if you charge a capacitor with no resistance in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? We would probably predict the capacitor to reach full charge faster. When the capacitor was directly connected to the battery, it lit up and charged almost instantaneously. When applied directly, the voltage goes immediately and directly into the battery with no resistance. In conclusion, our real-life experiment successfully supported the Kirchhoff's loop and node law and the idea of conservation of energy and charge. Additionally, we observed an RC circuit and displayed the time-dependent nature of charge flow. Thank you.